Introducing Gaussian hair modeling and rendering with light-aware Gaussians. Modeling the complicated hair with explicit geometry require extensive experience and labor with the traditional modeling tools or require expensive apparatus. Recent neural implicit methods have shown exceptional capability in modeling photorealistic hair and fur, but lack explicit geometric structures. Hybrid methodologies have adopted explicit strand geometry for hair animation, but they fall short in reproducing authentic hairlighting phenomena due to coarse geometric primitives or typically necessary neural renderer designs. 3D Gaussians, splatting, and adaptive shells have enabled detailed scene reconstruction, yet the structure of these primitives does not inherently conform to the filamentous nature of hair strands. We introduce Gaussian hair, an innovative explicit volumetric hair representation. First, we transform the elliptical Gaussian into a cylindrical Gaussian, and we attach each Gaussian to the core strand, which is the conceptualization of each hair strand as a sequence of linked, cylindrical-shaped 3D Gaussian primitives. Then we optimize their positions, orientations, and lengths through photometric supervision. To reconstruct Gaussian hair from images, we first propose to obtain accurate and clean 3D orientation fields by reconstructing directional segments with additional RGB supervision with cylinder Gaussian. Specifically, we optimize a randomly initialized geometry texture map, which can be decoded into a set of strands using a off-the-shelf MLP decoder. The 3D orientation field is then adopted to guide the generation of coarse strands. The Gaussian hair is then initialized by replacing the segments of the strands with cylindrical Gaussians and then optimized with photometric loss and additional regularization terms. We have also proposed the hair scattering model, and next we will provide a detailed introduction. To enable illumination effects, we further associate a simplified Martianer hair model with our optimized Gaussian hair to model single hair scattering function. RTT-TRT refers to three modes of the light scattering path through a single hair fiber, corresponding to reflection, transmission, reflection, transmission. To illuminate the interior hair, we primarily compute the attenuated light intensity from the light source to hair. We attach an additional transmittance term TR to each hair Gaussian and update the value by an extra fast light pass before rendering. Note that checking the intersection of a ray and a Gaussian is not trivial in 2D image space. Thus, we only regard the Gaussian of which 2D Gaussian contribution to the pixel is above a threshold as intersected. Due to the lack of authentic hair data in existing datasets, we have captured a real hair dataset using mobile phone. Each hair sample includes approximately 2,500 frames of 4K photographs, along with their Gaussian hair strands. Recognizing the diversity in hair thickness, curliness, color, and sheen across different regions, we enlisted models from various geographical backgrounds to photograph their real hair. Additionally, we employed professional stylists to craft a variety of distinctive hairstyles, enhancing our dataset with a vast array of styles. We also used colored hair wax to create hairstyles with mixed colors. Thus, our dataset has a wide distribution, covering different colors, lengths, and degrees of curl, such as loose hair, braids, waves, and dreadlocks. Here we show the qualitative comparison results. NOPC and MVP fail to achieve high rendering quality, and their training is inefficient. Convenerf recovers high-frequency details but lacks realism in hair detail. Clear artifact can be observed when zooming in. 3D Gaussians tends to have blurry artifacts due to their imprecise hair geometry, especially at the boundary region, where we may observe the existence of unorganized Gaussian kernels. Once reconstructed, our method naturally facilitates a variety of editing. We can naturally adjust the length of strands, change the hair properties such as roughness, as well as alter the hair base color. We can further simulate the complex lighting effects, such as reflection, refraction. We can also render with either ordinary composite lighting or film-style illuminations. This enables our work to be further seamlessly integrated into the production workflow of the conventional CG pipeline. Thanks to our reconstructed explicit strands, we can also achieve hair animation and simulation. Thanks for watching.